The third exercise in the Promax Foundations course covers a simple MDEA sweetening unit. The goal is to reduce the acid gas content in the inlet sour feed to less than 2 mol% carbon dioxide and less than 4 part per million hydrogen sulfide using a 40% MDEA solution. To start, let's set the environment. When I select Active Environment from the menu, or the blue Erlenmeyer flask on the toolbar if you're using a different version of Visio, I'm given the environment dialog. First, let's select one of the amine sweetening property packages, either Pang-Robinson or SRK for the vapor phase, depending on your project requirements. Let's choose Pang-Robinson for this exercise. This is an electrolytic environment, meaning that Promax will predict ionization within the liquid streams, in turn allowing all of the required interactions and reactions to occur for the system. In the Components tab, we should include all of the components of the inlet gas, plus the amine and water. Once this is done, we should close this dialog by selecting OK. Next, let's specify the inlet gas stream. We're given the inlet conditions of 100 degrees Fahrenheit, 1000 psi, and 50 million standard cubic feet per day. We're also given the inlet composition, which includes 1.5 mol% hydrogen sulfide and 3.5 mol% carbon dioxide. You can see here that this stream is being specified on a dry basis, the same as most prepared compositional analyses. Since this stream is really saturated with water, we will allow Promax to calculate the amount of water that is present. This is done in our saturator block. We must go to the saturant stream here and set the composition to be 100% water. The temperature, pressure, and flow rate required for the stream will be calculated by Promax. If we double-click on the saturator, we can see that it is currently set to saturate the stream to 100% saturation, which is what we desire in this case. If we execute the block, we can see that the outlet stream has the same temperature and pressure as the dry gas did feeding it. Promax will calculate the required temperature in the saturant so that once mixed, the outlet temperature is the same as the inlet. Since there is a heat of mixing that affects the mixed fluid temperature, you can see that the saturant stream is at a much higher temperature than the outlet gas temperature will be. Since the column cannot solve until it knows all of its inlets, we must correctly supply it a starting point for the amine stream that feeds in. This is accomplished by giving the recycled block its required guess, and then solving towards the column. The recycle block guess always goes in the outlet stream from the recycle. It must be fully defined by you, the user. There is no exception to this rule. The stream on the outlet must become green by your guess. This means we must typically provide a temperature, pressure, flow rate, and composition guess. It's important to remember that this is a guess and will be overwritten as Promax solves through the project. For this specific case, a good guess is the known flow rate of amine, 190 standard gallons per minute, a pressure close to what the regenerator is operating at, about 15 psig, a reasonable temperature guess, 100 degrees Fahrenheit, and a composition guess based on the circulating amine, 40% amine and 60% water. This then feeds to the makeup blowdown block. This block has a very specific method on how to specify it, but it's important to first know why it exists. The system is an open-loop system, which allows several places for your solvent to be lost. This necessitates a makeup to maintain a constant flow rate and circulation. An amine solution, however, is a mixture of amine and water. The losses are not equal between the two parts, as water is lost much more readily in the system than the amine is. Therefore, a relatively large amount of water must be made up compared to the amine, but there is no easy way to know exactly how much of each must be made up. It will change with any change in the operating conditions or flow rates. Promax can calculate the required flow rates of both parts of the system as long as it is given the correct information in this block. First, we have a desired circulation rate for the solution. in this case 190 standard gallons per minute. This should be set at the outlet of the makeup blowdown block. Promax will then add as much makeup as required to get back up to this flow rate. In some cases, Promax might be required to blow material down to get to this flow rate. This is common if you're adjusting the amine flow rate and the recycle gas is still at a higher flow rate. In general, this is not anything to be worried about unless the final solution indicates that there is blowdown. Setting this flow rate satisfies the first of two required specifications for the block, the one that allows Promax to calculate the flow rate of the makeup stream. We still must provide the information Promax needs to calculate what the composition needs to be. This is accomplished from within the block. Under the Process Data tab are two columns, titled Target Outlet Composition and Makeup Bulk Composition. Selecting Edit will let us place the required values in their fields. What we want is for the outlet stream from the block to have a composition with 40% MDEA exactly, so we will set this in the Target Outlet Composition blank. It is tempting to place a 60% for the water, but this is incorrect. If you were to tell the outlet composition to be 40% MDEA and 60% water, Promax will solve to this exactly. In reality, there are some residual acid gases that will be in the stream, since the regenerator is not perfect. We allow these impurities from a practical standpoint, and we must allow Promax the freedom to allow them as well. If we put 60% for the water, Promax will have no choice but to blow down 100% of the regenerated amine stream because it has impurities in it. It will then make up 100% of the circulation rate to continue with the process. This is not what we want Promax to do. Instead, we leave water blank in the target outlet composition column and say instead that the makeup bulk composition is 100% water. Promax will now solve first by looking at what is in the inlet stream, then adding any required MDEA to obtain a 40% outlet composition, while also adding pure water to obtain the required flow rate in the outlet stream. In the end, there are 2 degrees of freedom with 2 variables. The MDEA and water flow rates in the makeup stream solve for the outlet composition of 40% MDEA with a flow rate of 190 standard gallons per minute. Since Promax will be mixing the required stream with the inlet stream to the block, we must give it a temperature and pressure. I typically use something slightly above the inlet stream pressure and a reasonable ambient temperature. We'll look at the results of our specifications in the next tutorial. For now, let's move on downstream. Next is a pump. We should include the efficiency, probably about 65%, and an outlet pressure. This pressure should probably be the same as the inlet gas stream, plus some extra pressure to account for the upcoming pressure drop across the air cooler. I'll make this 1000 psig. The air cooler should have a pressure drop set. I'll use 5 psi. The outlet temperature is also set. I'll use 110 degrees Fahrenheit. A typical rule of thumb is to keep this temperature approximately 10 degrees above the inlet gas temperature to minimize hydrocarbon condensation and foaming issues. Now we can take a look at the absorber. The column has been set up using 7 ideal stages. Since the real to ideal stage ratio is typically 3 for an amine absorber, as detailed in the previous tutorial, this corresponds to approximately 21 real trays. Now, on the Process Data tab, we should set this to be a T-Suite Kinetics tower type. On the Stage Data tab, we should first set a pressure profile for the tower. I'm just going to set a pressure change of 5 psi and allow the inlet pressure to set the column pressure. Since we are using the T-Suite Kinetics model, we must provide the information required for Promax to calculate the residence time in the column. Selecting the hardware grouping option here on the left, we can first set the general tab information. I'll set the diameter at 4 feet and copy this to the bottom. Then, I'll set the real to ideal stage ratio at 3, and I'll also set the system factor at 0.8 for this column. For a trade tower, leave the residence time blank to allow Promax to calculate what it will be for your specific case. If you have verified data that indicates it is different than Promax predicts, then you may overwrite the values given by Promax. Switching to the tray tab, I can set the last information required, the tray spacing at 2 feet, and the weir height at 3 inches. Once this is complete, the tower should be ready to solve. If you see any warning messages that indicate an equilibrium tower type is being used, there is a piece of information missing that is required to use the kinetic model, and your result will be inaccurate. The warning should explain what the missing information is, and once you have added any needed values, you should resolve the column. We are then given that the rich flash tank operates at 100 psi. I can set that in either of the outlet streams, or calculate what the pressure drop required to obtain that outlet pressure is, and use that as a block specification. In general, it's better to set the outlet pressure so that it is maintained even if upstream conditions change. I'll set the pressure in the outlet flash vapor stream here. We're told that the rich amine enters the regenerator at 210 degrees Fahrenheit. This should be set here in stream 3. However, the heat exchanger that controls this temperature also has a pressure drop associated with it. Since this is a two-sided exchanger, there are two process sides, most likely a shell and a tube set, that will each have an associated pressure drop. I'll use 5 psi for each. This is set within the exchanger process data tab, here for side A and here for side B. We can now solve everything in the project, excluding the regenerator and its add-ons, the condenser and reboiler. The stripper has 10 stages set up, which corresponds to about 20 real trays, since the column efficiency for an amine regenerator is approximately 50%. Next, the column type should normally be T-Suite alternate stripper. There are some cases where T-Suite kinetics should be used instead, such as any case involving a thermosiphon reboiler. For more information on this, please consult the Promax help. Next, we need to set the column operating pressure. I'll do this by setting the top stage at 12 psi-G and giving a 4 psi pressure drop across the column. By using the alternate stripper model, we do not need to set any additional hardware information. We do have 2 degrees of freedom remaining for this column, one each from the reboiler and the condenser. We're told that the reboiler duty is 17 million BTU per hour. We can set that directly in this energy stream. Verify that the units are correct. If you type the value in first, then change the units, Promax will do a unit conversion, giving a much different result. Once we have this correct, we should go back to the column to set the second specification. From the Specifications tab, we should add a new specification. Select Phase Property from the list given, since the temperature we're trying to set for the condenser is a property of a phase of one of the associated streams of the column. We can rename this Condenser Temperature, and then select OK. Choose the stage, Condenser, then the phase. I'll choose Tool, although any will work for the flash properties, and then select Temperature. Give this the target value of 120 degrees, and leave the tolerance blank. You should not set the tolerance here unless you have a very good reason, typically only if suggested by our support staff. Click Active so that Promax will use this specification towards one of the degrees of freedom in the column. Once we've done this, the project should be ready to run. Click Execute Project and wait for the entire project, including the recycle block, to turn green, and for the message log to show that the solve has ended. The following tutorial will step through answering the questions for this project, including an explanation on amine loading and lean and rich approaches in the contactor.